Hi guys, so in this short video then we're going to be working with the data set in SPSS that we set up earlier to perform an ANOVA test. Okay, so this is the data we set up earlier. Alright, so we've got treatment, we've got 3 different treatments, okay, and we've got data on a physiological variable in those 3 different treatments, S1, S2 and S3. Okay, and remember S1 data comes from sample population, which is independent of the data taken for S2, which is again independent of the data taken for S3. Okay, so it's independent samples data. All right, and we've set that up accordingly. Okay, so we've got the data in one column and treatment signified in another. Okay, and we've set our values and given them labels, and we've also set our measures up correctly as well. So our data, our physiological sample data are scale data, and our treatment data are nominal because they are the categories. Okay, right. So first of all then, like I say, we're going to be performing an ANOVA here. And we know it's an ANOVA because the data are parametric. They conform to the assumptions of a parametric stats test. Okay, so for example, they are normally distributed. So we can just check this again here. I've checked it earlier, but we can just go through the motions and check it again here. So if we just go to explore, put the data into the dependent list, and treatment is the independent factor, so that goes into the factor. Okay. We're just going to check histogram and check normality plots with tests. Okay. Okay, so this is going to give us our normality test output, and from here if we look at the Shapiro-Wilk test, because we've got quite small sample sizes, we can see that all of our p-values are much higher than 0.05. It's non-significant. So our data are not different from a normal distribution. Okay, so we've got normally distributed data, hence why we're performing an ANOVA. Okay. Okay. So in order to perform an ANOVA, it's pretty straightforward. Okay, we go to Analyze. Because the ANOVA compares means, we go down to the drop down for Compare Means, and simply we select one-way ANOVA. Okay, and like we just did with the running the normality test, we put our actual data, the dependent variable in a dependent list, and treatment, which is our independent variable, into the factor list. Okay. From here we can just press OK, and that will run the one-way ANOVA for us. Okay. This is our ANOVA output. Pretty straightforward. Okay. So the things we're interested in here then is this top group. So this is the output, the statistics output that we're interested in. So between groups. Okay. So what we're interested in here. Sorry, we're also interested in this within groups bit as well, okay, but mainly this top bit. So what we're interested in here are the degrees of freedom, the F statistic, and the actual p-value statistic given here. Okay, so when we report the results for an ANOVA, for the degrees of freedom, we report 2 numbers actually. So we report this first one here for between groups. Okay, so the 2. Remember, the degrees of freedom signifies kind of information about sample size in this. Okay, so the 2 actually represents how many categories we were looking at. So we had 3 categories in total. Degrees of freedom for that is calculated as total number of categories minus 1. Okay, and the within groups here. Okay, 15. This is the other number we're interested in because this tells us about the whole the complete sample size that we had. Okay, so we had 18 individuals in total, but we minus 1 for each category, and that gives us our within groups degrees of freedom of 15. Okay, so these are the 2 numbers we're interested in. Okay, the other one is the F statistic, so that gives us our statistic we're interested in that we need to report in a results section, and then the significance value of 0.003, which, as we all know, is highly significant. So if I was going to write this result out, it will look something similar to this. Okay, so it will be ANOVA. I would give my F statistic. F equals what was it? 9.08. 9.08. The degrees of freedom and then the p-value. I'm going to put less than 0.01 because that's the correct threshold. Okay, it's not less than 0.001, but it is less than 0.01. Okay, so if I was going to write this result out, it would look something similar to that. There are different ways of writing it, but just for simplification purposes, that's how it would look. Okay. Okay. So what this result indicates then is that we do have some differences between the means and the variation between the means in our data set. Okay, so maybe one of the groups or two of the groups are different to the others. Okay, but it doesn't tell us here which ones are different. We've got three groups here, remember. When we run a test for differences with two groups, it's easy. If we get a significant result, we know that one is higher than the other. We just need to look at the means to see which one is which. But when we have three groups, it's a little bit more complicated than that. So we need to do what you call a post hoc test. Okay, so this is pretty straightforward to do. So if we go back to analyze and go compare means again and select one-way ANOVA, here we just want to select post hoc. Okay, and this will give us an option to select the post hoc test. The one we use as standard is the 2 key, so we're going to select that, and then we're going to press continue, and then hit OK. And now what we're going to get now is our ANOVA result again, but below this we're going to have our post hoc test, which tells us where the differences actually are. So in the ANOVA we know there is a significant effect somewhere in this data set, but we don't know where. The post hoc test will tell us this. But this table here is our post hoc result. Okay, and basically what we've got going on here is multiple comparisons between treatment 1 to S1 and S2 and S1 and S3 given here. If we follow this along with a significance value, we can see that the difference between S1 and S2, there is no significant difference. But if we look at the difference between S1 and S3 and follow that along to the sig value, we can see that there is a slight significant difference. Okay, 0.048. Okay, so we know that there's a difference between S1 and S3. If we go on to the next lot, we can then, the difference between S1 and S2 is given here, so that's duplicated as above. Then we've got S2 and S3 here. And here we can see this is highly significant, so the difference between S2 and S3 is highly significant, 0.002. And this bottom one down here is just a duplication of all of that above. So we've got S1 against S3 here and S3 against S2 here. Okay, so it's all just duplicated as above already. Okay, so yeah, from this we know that we've got a significant effect overall from our ANOVA test, and then from our post hoc test we know that there's a significant difference between S1 and S3 and S2 and S3. So lastly then we want to make a graph just so we can visualize this. Okay, and this is pretty straightforward. It's similar to how you made your graph last time when you had a test of differences between two groups. We just go to graphs and chart builder. Because we're comparing means, we use a bar graph with error bars. So we just move that option up to here. We put our data, which is our dependent variable on the y-axis, and our treatment, which is our independent variable on the x-axis. Okay, we need to tell it to display error bars, and remember we want to show the standard error bars because this is what the test uses, and we need to change the multiplier to 1. and then we just hit OK, and there we have it. We have our bar graph with error bars showing our result. Okay, so if we just recap on what we found earlier, overall, the ANOVA picked up an overall difference. Okay, there's an overall significant effect within this data set, and the post-hoc test indicated that there was a slight significant difference between S1 and S2. Okay, p-value of 0.048. I think it was between S1 and S2. Hang on, let me just double check that. Oh no, sorry, my mistake. S1 and S2, there was no difference. The difference between S1 and S3, p-value 0.048, and a highly significant difference between treatment S2 and S3, a p-value of 0.002. Okay, or 0.003, one of those. No, 0.002. Okay. Okay, so that's it. So now you kind of know how to run an ANOVA. You can have a go now doing this on the questions in your assignment.